Chapter 18 review. The figure below shows the probability histogram for the total number of spots when a die is rolled 8 times. The shaded area represents the chance that the total will be between 20 and 25. And in general, when do we need to use the histogram, the edges of the columns in the histogram? When you have a low number of draws. Hey, you do. Did you catch that? So number 1 is 20 to 25. So in this case, do we need the edges? So this is the probability histogram, and we're only rolling 8 times. Yeah, we're going to need the edges. 8's not very big. So it would be 19.5 to 25.5. Sorry. So if you have a low number of draws, then the edges, and technically they're not needed, they'll just be more accurate. So how many draws is a lot? It depends. 1,000,000 is usually a lot. But if your box only has 2 numbers in it, then 400 is a lot. But if your box has 600 numbers in it, then you might need to do something like 10,000 draws. So you just kind of play it by ear. The edges will always work. It's just more effort. But as you approach the normal curve, you can stop worrying about the edges. Okay? So number 2, 400 draws will be made at random with replacement from that box. Is 400 a lot? For a box with numbers 1 through 7, 4 of them? Yeah, 400 is probably quite a few. Okay, estimate the chance that the sum of the draws will be more than 1,500. So we need the average of the box, which is? What's the average of the box? 4. Okay, and we're making 400 draws. So the EV is 1,600, give or take. Well, we need the SD of the box. Can I use the shortcut? No, why not? There are more than 2 different numbers in the box. So I find the SD of the box, and I get 2.2. What does that mean? Nope. The numbers in the box are on average 2.2 units away from 4. Okay. Now I find the SE by taking 2.2 and multiplying it by the square root of 400. So that's 20. 2.2 times 20 is 44. So this plus or minus 44. 68% of the people will be inside that interval. Okay, so the chance that the sum of the draws will be more than 1,500. We draw a normal curve. Can I use the normal curve? Yeah, 400 draws is quite a few when we only have 4 numbers. So I'm just going to not use edges. Can I use edges? I can use edges, but the difference between edges and no edges is going to be so small, it's not going to matter. No, the average, or the expected value is 1,600. We want to know 1,500 or bigger. So we want this area here. Okay? So how far off am I from the expected value? 100. And then 100 divided by the SE will tell me my z-score. Oops. So my z-score is negative 2.2. It's okay. You got the same answer. Did you shade to the left or the right? If you shaded... Yeah. But if you shaded the wrong direction, you're going to get the wrong number. Oh, you did? You just flipped the whole thing around? That's fine. Okay, clear my draws. Go into my distribution, shade norm, lower bound, negative 2.2, upper bound, 5, comma 0, comma 1. So I ended up with 98%. Can I use the z-score table in this case? No, why not? We're not finding middle area. Now, there is a way to do it, but it just takes a lot more effort. So your expected value is the average. It goes in the middle. Your EV always goes in the middle. Right. Yeah, that's what you're supposed to do. Oh, no. No, and then you just made it negative, right? So you fixed it. You ended up fixing it. Yeah, you're supposed to do expected minus, or sorry, you're supposed to do value minus the average. You just flipped it around. Well, that's our answer. Okay, estimate the chance that there will be fewer. So the answer to 91 is 90, or sorry, the answer to number A is 98%. Okay, now for B, we have to change the box. Okay, in B, we change the box. Okay, we no longer have 1, 3, 5, 7 in the box. What do we have? So we're going to play a game, and it's called If You Get a 3, You Win. Right? If you don't get a 3, then you lose. So the box now has 3 zeros and 1 1. So when you add the box together, the box contains the original numbers. If you're counting specific values, then you play the win-lose game. Right, there are 4 tickets in the box still, but why do I only have 1 1 in there? There's only 1 3. And then the other 3, we don't care what they are. So basically what we're doing is we're adding up the number of 3s. The actual value of 3 is not important. The fact that we got the 3 is important. Right, exactly. All right, so find the chance that there are fewer than 93. So we're playing 400 times. What's the average of the box? 0 plus 0 plus 0 plus 1 divided by 4 is 0.25. What does that mean? That is the expected value per draw. Now we multiply that by 400. 0.25 times 400. And 200. What does that mean? Oh, yeah, that's not right. 0.25 times 400. That ended up definitely being too large. So 100. What does that mean? If you draw from this box 400 times, you would expect 100 threes. Okay? The SD of the box, can we use the shortcut? Yes, 1 minus 0 is 1 times the square root of 1/4 times 3/4. So the square root of 1/4 times 3/4, not sevenths. So 0.43. What does that mean? The tickets in the box, on average, are 0.43 units away from 0.25. Okay? So if we make 400 draws, our SE is going to be 0.43 times 20. Okay? So what do I know about playing this game 400 times? You expect to get 100 threes, give or take 8.6 threes. Okay? Can we use the normal curve? 400 is quite a few when compared to 4 tickets. So we draw the normal curve. Oh. You can't. Which is why small number of draws really mess things up. What that means is as we make lots of draws, then it will approach point whatever per ticket, right? But if you make one draw, there's no way to get that number. So that's just, on average, we would expect that many. No, that doesn't count. All right, what were my numbers? My smartboard died. So I ended up with 100 plus or minus 8.6. So normal curve 100, and I want to know 90, which is a gap of negative 10. Oh, so we want this side? Okay. Do I need to worry about edges? No, 400. For this box, 400 is quite a few. So negative 10 divided by 8.6 gives me a z-score of negative 1.16. Now I need to clear my draws and shade norm from the left side until negative 1.16. Second variables. So I ended up with 12.3%. Okay. Wow. There's no way we're going to get through all this today. That's okay. All right. 3. 10 draws are going to be made at random with replacement from the box 0, 1, 2, and 3. The chance that the sum will be in the interval from 10 to 20 inclusive equals the area under the normal curve or the probability histogram? The probability histogram. How come? We have a small number of draws. Between which two numbers? 9.5 to 20.5. Okay? And we have to include the edges because 10 draws is just way too small to be very accurate on the normal curve. Okay. 4, a coin is tossed 25 times. Estimate the chance of getting 12 heads and 13 tails. Now this one's kind of misleading. So what is in the original box, instead of flipping coins, I'm either pulling out an H or a T, right? But H and T's are not numbers, right? So we will say a 0 means we lose, so that would be we want heads, right? Well, I guess it doesn't matter. You pick whichever one you want. So we're going to convert this box into 1, 0. Okay. And we're making 25 tosses. What is the average of the box? 0.5, which means we expect to win 50% of the time. And the SD of the box, how far away are those numbers from 1/2? They're both 1/2, so I don't even need to calculate it. The SD of the box is also 0.5. What did you do? I got 1 instead of 2. Oh, that's the one you were asking me about, right? So it's going to be 1 minus 0 times the square root of... Oh. Well, you put -1 because you were looking at losing $1 and winning $1, but there's no betting here. We're just counting H's. If all you're doing is counting, then you do 0 and 1. If you're betting, it would be 1 and -1. Okay. So my expected value in 25 draws is going to be 12.5, right? My SE in 25 draws is going to be 2.5. right? So it says 12 heads and 13 tails. Do I really need all that? No, because if you get 12 heads, then you have to get 13 tails. So we really just need to count up the number of heads or count up the number of tails, but we have built our box to count heads. So the expected value is 12.5, and we want to know exactly 12, right? Do I need to count edges? Yes. Why? 25 is small, but there's another reason why I have to count edges. Exactly 12. Right? If we don't count edges, we find the distance from 12 to 12, which is 0. So we want 11.5 and 12.5 turned into z-scores. So that would be from 12.5, that's -1 and sorry, so this is 12. -1 and 0, right? So let me draw the histogram. Come on. Are you kidding? What's going on? I don't know why that's not working. All right, well, I'll just draw one up here. So over here is 12, and I want to, and then the average is 12.5. The expected value is 12.5. So I need to go from 11.5 to 12.5. Well, 12.5 is the expected value, so the z-score is 0. So I really just need to go from, I need to convert -1 and 0 into z-scores. I wish I could get a new page. Oh, sure, now all of a sudden it works. I didn't even do anything. Okay. Now that I can draw this bigger, okay, that's the expected value, right? Plus or minus 2.5, right? So I want to know what is the column that surrounds 12. Well, we go left to 11.5 and we go right to 12.5, which is the expected value. So we're going to calculate those two edges. How far away is this edge from the center? Right. So -1 is our distance for our left edge. What's the distance for our right edge? No, from how far is it from the middle? 0. It is the middle. So we want this area here, right? Well, to find a z-score, we have to compare it to the EV. The left side is one head away from the EV. But the right edge is the EV. So to find my z-score, I divide them by 2.5. The SE. So -1 divided by 2.5 is -0.4. So I want to shade norm from -0.4 to 0. Can I use the table? Actually, in this case, you can. You just look it up and cut it in half. So we look up 0.4. So 0.4 is 31%. So it's going to be 15.5. Right, the other half we don't need. Yeah. So for some reason that 0 is really messing you guys up. Okay. So what if it was this? Let's say 13, and I want 12. So that would be from 11.5 to 12.5. So how far, we want this area, how far is that? Negative 1.5. Okay. How far is this? Negative 0.5. So we would z-score both of those and then do shade norm. Okay? Does everybody get that? Well, in this one, the right side is the expected value. So the z-score is automatically 0. The left side of that column is 1 unit away. The right side of the column is the expected value, so the z-score is 0. Well, you could do shade norm here, but I was too lazy, and I just said, well, this area right here can be found in the chart, and then I just cut it in half. Because the right side and the left side are the same size. So whenever you can use the chart because it speeds things up. But you could just do shade norm from negative 0.4 to 0. That's fine. It doesn't matter. All right. 5. 25 draws are made at random with replacement from the box 1, 1, 2, 2, 3. One of the graphs below is a histogram for the numbers drawn. One is the probability histogram for the sum, and one is the probability histogram for the product. So number 1 would be the probability histogram. Okay? That's what happens if you make a lot of draws. Okay? 2 is going to be the product histogram, which is totally useless. And then 3 is going to be the numbers drawn. So number 1 is the sum. We're adding things up and then creating a probability histogram. Okay? 3 is just the probability histogram for how many 1s and how many 2s and how many 3s there are. And that was just... So number 3, well, yeah. All you really need to know, as long as you understand that that the histogram for a certain number of draws will approach the probability histogram if you draw enough, then you're fine. Okay. You also need to know the difference between... So if we do 100 draws or 200 draws or 1,000 draws or 1,000,000 draws, the more draws we do, the histogram that you get from the number of draws, the sum of the number of draws, will approach the probability histogram. Right? The probability histogram is sort of the expected amount. Okay. You also need to know the difference between adding up numbers and counting numbers. If you're adding up numbers, then you would use 1, 1, 2, 2, 3. What if we were counting the number of 1s? What would be in the box? 2 1s and 3 zeros. If we're counting the number of 1s, 2 1s and 3 zeros. What if we're counting the number of 2s? 2 1s. Because we don't care how big it is. We just want to know how many there are. What if we're counting up the number of 3s? 1 1 and 4 zeros. So that's really what the difference that you need to know. 6. A programmer is working on a new program, Coin, to simulate tossing a coin. As a preliminary test, he sets up the program to do 1,000,000 tosses. The program returns with a count of 502,000 heads. The programmer looks and thinks, 2,015 off. That's a lot. No, wait. Compare it to the million. 2,000, forget the 15, out of 1,000,000 is 2 out of 1,000. That's 1 in 500, 1/5 of a percent. Very small. Good. Coin passes. So what we need to do is set up a box. What's in the box? A 1 and a 0. Okay? So the average of the box is 0.5. The SD of the box is 0.5. If we do 1 million draws, we would expect to get 500,000 H's. Give or take 0.5 times the square root of... Right. We would expect 500,000, give or take 500. The SE is 500. Now, let's stop. We don't need to go any further. Is something wrong with his game? Yes. Why? He was over 4 SDs away from the expected value. Right? So his game is messed up. So this is 500,000, right? He ended up with 502015. Okay? How far is that? 2015. But the SE is 500. So that's a Z-score of 4 plus. So what is the chance that his game is okay? Well, it would be like 0.001%. So we're going to go ahead and say, no, something's wrong with your computer. Your game is not fair. Okay. Pair of dice are thrown. The total number of spots looks like a draw from the box 2 through 12. The sum of the two draws from the box 7. So a pair of dice are thrown. The total number of spots is like one draw from the box 2 through 12, or the sum of two draws from the box 1 through 6. Which one's right? So we rolled 2 dice. We rolled 2 dice. How many possibilities are there? 2 through 12, but there are 36 possibilities. So is the top box correct? No, because there should be 2 3s and 3 4s and 4 5s and 5 6s and 6 7s. So the top box is wrong, but the bottom box will work.